All right, everybody, welcome back. So now I guess it's time for part 2 of integration in spherical coordinates, although I think this should be the third video in the list of ones for section 15.8. So I guess now that we have the formula for how to do integrals in spherical coordinates, let's do some examples. So let's let E be the region of space that is enclosed between the two spheres, x squared plus y squared plus z squared equals to 9, and x squared plus y squared plus z squared equals to 16. Now we know, now that we have spherical coordinates in our toolbox, we can describe these spheres in much nicer equations. Namely, the first one is the sphere rho equals to 3, and the second one is the sphere rho equals to 4. So perhaps we might even just step off to the side for a second and look at GeoGebra. As we can see here, this is the sort of region that we're talking about. We're talking about the region that's inside this sort of gray sphere, but outside this red sphere that's inside. You notice this is kind of an interesting region. If you project it to any of the sort of coordinate planes, what does it look like? But it looks like maybe an annulus, right? When you do this projection to one of the planes. Remember, an annulus was the region of a plane that's in between two concentric circles. So this is just the three-dimensional kind of spherical version of an annulus, this region that we have E here. So let's see how we might model that with spherical coordinates. Well, it looks like the radii, rho, go between 3 and 4, and the thetas go all the way around, because we go all the way around in the xy plane there, and the phis go all the way top to bottom. We get the upper hemisphere from having phi from 0 to pi over 2, and the lower hemisphere from having phi go between pi over 2 and pi. So it looks from the way that we've written it here, all the bounds in question are constants. So this space is one example of a spherical box, which I guess is nice because we have that it's the sort of spherical analog of an annulus, and an annulus was a sort of polar box. So there's interesting parallels here between spherical coordinates and polar coordinates, just like there were interesting sort of parallels between cylindrical coordinates and polar coordinates. So there's a lot to kind of ingest and think about, but we'll just go forward. So now that we've got this space E modeled as a spherical box, maybe we'll try to compute its volume or something. But I think you might recall the volume enclosed by a sphere of radius rho is given by this formula V equals to 4/3 pi times rho cubed. If you don't remember that formula, don't worry, because now you have the power of integration in spherical coordinates to compute volumes for you. So you don't need to memorize silly formulas. But if you do recall this formula, you might actually then think that we can predict exactly what the volume of this region of space is going to be. We'll have 4/3 times pi times the difference of the outer radius cubed minus the inner radius cubed. So that turns out to be 4/3 pi times 37, which is 148 pi over 3. So now that we have what we expect to be the volume of this sphere by just formulas that we were handed in our youth, let's actually compute the volume using a triple integral. So how do we compute volumes via triple integrals? Remember, the function that we integrate is the constant function, f of x, y, z equals to 1. But because we're going to use spherical coordinates, we'll need to multiply 1 by the spherical coordinate Jacobian matrix determinant, which is rho squared times sine of phi. So here's this computation here. The volume of E will be given by the integral from 0 to 2 pi of the integral from 0 to pi of the integral from 3 to 4 of the function 1 times rho squared sine of phi. This is that Jacobian determinant. And we'll do the rho integral first, the phi integral second, and the theta integral last, although Fubini tells us that it doesn't really matter which order we do these in. So here we go. It looks like the rho integral is just 1/3 rho cubed, and so we'll evaluate that one at 4 and 3 and take the difference. and we get 37 over 3. That's promising. I've seen that on the previous slide, right? And then what we still have left over here is sine of phi, and that's what we'll integrate next. So integrating sine of phi, we get negative cosine of phi. And we'll evaluate that one at pi and at 0 and take the difference. Well, let's see. Negative cosine of pi is negative 1, which is 1. And minus negative cosine of 0 is, again, plus 1. So here we get 2 coming out of here. So we get 37 over 3 times the integral from 0 to 2 pi of 2 with respect to theta. And since there's no thetas here in what we're integrating, we're just going to slap a theta on and evaluate it at 2 pi. So in effect, what we get is 37 over 3 times 4 pi, which is 148 pi over 3, as we'd expected. So that wasn't so bad. Let's do more. So now let's let E be the region of space that is bounded below by the cone z equals to the square root of x squared plus y squared, and bounded above by the sphere of radius 1 centered at the origin. So we know some nice equations now in spherical coordinates for both of these guys. In fact, they're both given by one variable equals to a constant, right? So let's look at this shape first. So here's the shape in space. So we have, it's bounded below by this cone. So the space in question is all the stuff that lives above that cone, but then below this sphere, right? That's the sort of difference of terminology. So the lower bound is this cone, and the upper bound is this sphere, and the region in question is all this stuff that's in here. Okay, now we know the equation of that cone is given by phi equals to pi over 4, right? I think we saw that in one of the previous videos. I think it was the previous video to this one. And we also know the equation of this sphere is rho equals to 1. So then let's think about this region of space in spherical coordinates. Let's say that for each phi, let's say we start at phi equals to 0, that's this line here along the z-axis. It looks like the radii go from 0 out to 1, right? And then as we move phi along a little bit, the radii still go from 0 out to 1 at the edge of this sphere. And in fact, even as we keep moving the phi a little bit larger and larger, the radii rho still go from 0 at the origin here, all the way out to rho equals 1 at the edge of this sphere. And even the last place we end with phi is phi equals to pi over 4. And at phi equals to pi over 4, we still go from rho equals 0 to rho equals to 1. And so all the while, the thetas go all the way around the xy plane, right? Or the plane that's parallel to the xy plane here. So it looks like that we can model this region E as the set of rho theta phi, where rho goes between 0 and 1, theta goes between 0 and 2 pi, goes all the way around, and phi goes from 0 at the z-axis to pi over 4 out here. And so yet again, we have that this region's bounds are all constants. So this is yet another example of a spherical box. Let's see, we might stop and think about what this is analogous to from, say, polar coordinates. I think one example of a polar box was, say, to have a sector of a disk in the plane. This, to me, looks like it's sort of a sector of a three-dimensional ball. And so this is, I think that's a nice way to think about it. And so if that's confusing to you, then let's talk about it. But I guess we can't really talk over this video. So this is, we can think of this guy as a sort of sector of a three-dimensional ball. I would probably call that a three-dimensional disk, but that's just me. Whatever. You might think that if we let phi vary all the way from, say, 0 to pi, we would get this whole spherical ball, everything included inside that sphere. So, so this is analogous in some sense to the sort of polar coordinate polar boxes. It's just that they look a little bit more funny now in space. So let's compute this guy's volume, I guess. Oh, no, actually, no. We have this a different example. Let's let f of x, y, z be z. Okay, so this is going to be the function that we'll have over this region E. So let's compute the triple integral of this function, f of x, y, z equals to z, over this spherical box. So we have the theta integral goes from 0 to 2 pi, and the phi integral goes from 0 to pi over 4, and the rho integral goes from 0 to 1. And again, z, that guy is written in spherical coordinates as rho cosine phi. And because we've done this transformation into spherical coordinates, we have to multiply by the spherical coordinate Jacobian matrix determinant, rho squared sine of phi. Okay, so then we can combine like terms in our integrand here, and we get what? Rho cubed times cosine of phi times sine of phi. And so the rho integral becomes 1/4 rho to the 4th, which when we evaluate at 1 and 0 and take the difference, we just get 1/4. So we'll go ahead and yank that out. And now to do the phi integral, we have the integral from 0 to pi over 4 of cosine of phi times sine of phi. So this one I think we can do by u substitution, or you might invoke a trig identity if you like. I'm going to just do u substitution. So I'll let u be sine of phi, and so then du is cosine of phi d phi. And if I'm going to change to the u close, then I've got to change the bounds. So u of 0 is sine of 0, which is 0. And u of pi over 4 is the square root of 2 over 2, which for some reason when I was making these slides, I decided I liked better as 1 over the square root of 2. Don't ask me why. Well, maybe we'll see. So then the integral in question becomes 1/4 times the integral from 0 to 2 pi times the integral, or of the integral from 0 to 1 over the square root of 2 of now u du d theta. And that u integral is now 1/2 u squared. And when we evaluate that one at 1 over the square root of 2, we get 1/2, right? Okay, so maybe that is why I liked this as a better representation of this fraction. So now we get what? 1/2 times 1/2, that's 1/4. So we have what? Okay, well, we'll just leave that here. We have 1/4 now times the integral from 0 to 2 pi of 1/4 d theta. So we'll just slap on a theta and evaluate at 2 pi. We get pi over 2, right? And so then 1/4 times pi over 2 equals to pi over 8. So that is that's the answer for this spherical integral here. So then join us in the next one, where we'll talk about some spherical non-boxes. So we'll see you then.